All right, listen up. Welcome to today's strategy session. I am absolutely pumped for this explainer because we are tackling a mission that looks way more intimidating than it actually is: mathematical functions. Specifically, we're looking at the Cambridge 0580 syllabus. If you've ever stared at a hostile exam paper, seen a jumble of letters and numbers like f of x, and felt like you were trying to read a classified foreign language, you are in the right place. Today, your mission is to transform that abstract algebraic notation into a concrete, highly practical set of tools to extract maximum marks in minimum time. Think of it less like doing abstract math and more like operating a highly efficient factory machine. By the end of this session, you are going to have a complete, bulletproof function toolkit ready to deploy. Let's get to work. Okay, here is your mission briefing and our 4-step roadmap. First, deciphering function notation. Second, mapping domain and range. Third, finding inverse functions. And finally, combining composite functions. We're going in. Phase 1, deciphering function notation. Let's break the code. Before we can operate any machinery or extract any marks, we absolutely have to know how to read the manual. You'll see the standard layout all the time on your papers. F of x equals 2x minus 3. Now, sometimes examiners will try to throw you off by writing this as f, colon, x, an arrow, and then 2x minus 3. Do not panic. Let's demystify this right now. The f is literally just the name of our function, like giving a machine a specific name tag. It could be g, it could be h, it doesn't matter. The x in the brackets, that is the raw material we are feeding into it. So a massive mistake students make is thinking f of x means f multiplied by x. It absolutely does not. It is a direct command. It's the rule that maps an input, our x, onto a specific calculation, which right here is 2x minus 3. So the crucial point you need to lock into your brain is that a function is exactly like a factory machine. You have your raw material going in, that's your x. Once it's inside the machine, a very specific, unbreakable process happens. Maybe it gets doubled, maybe 3 gets subtracted from it. Then out pops the finished product on the exact opposite side. That finished product is our f of x. Thinking of it this way changes it from an abstract algebra problem into a tangible, physical process. It grounds your thinking, which is exactly what you need when the exam clock is ticking. Let's actually see this machine in action to secure those early method marks. If an examiner asks you to find f of 5 for our rule f of x equals 2x minus 3, you just follow 2 simple tactical steps. Step 1, substitute the input number 5 wherever you see an x in the expression. Write this down. Examiners love to see the substitution, so our raw material is 5. Step 2, calculate it. We do 2 times 5, which is 10, minus 3, which equals 7. The raw material was 5, the machine ran its process, and the finished product out is 7. Simple, reliable, and perfectly structured. Before we continue with the mission, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Phase 2, mapping domain and range. Let's secure the perimeter. Now that we know exactly how to run a single piece of material through our machine, we need to organize our warehouse. In Cambridge Mathematics, you have to use the correct terminology to show the examiner you know your stuff. We don't just say inputs and outputs. We use the official terms, domain and range. The domain is the entire set of your starting values. Think of it as your pile of raw materials waiting on the loading dock, ready to go into the machine. The range is the exact opposite. It's the set of all the finishing values. It's the final products sitting on the outgoing dock after the machine has completed its job. Domain goes in, range comes out. Keep that clear separation locked in your mind. And this brilliantly illustrates exactly what we're talking about. This mapping diagram is such a fantastic visual tool because it shifts your brain out of purely algebraic reasoning and directly into spatial reasoning. It's like a satellite map of our operation. You can visually see the domain oval on the left, our inputs like -1, 0, and 1, and you literally follow the arrows through the function. In this case, the process is 5x plus 2, to land safely in the range oval on the right, hitting the exact targets, -3, 2, and 7. It's a literal map of what the machine is doing, step by step. While we're observing these connections, there is a golden rule from the source material we absolutely must highlight because examiners love testing this. The rule is, functions can be 1-to-1 or many-to-1, but never 1-to-many. What does that actually mean on the ground? It means one single piece of raw material cannot magically turn into two completely different products. If you put a 5 into the machine, it can't simultaneously output a 7 and a 20. That's chaos. A mathematical machine has to be 100% predictable. If it's unpredictable, it's a broken machine, and in math, it's simply not a valid function. But following all these arrows pointing from left to right naturally begs a fascinating high-value question. What if we have the finished product, the output, and we want to go backwards? What if your mission is to reverse engineer the process to figure out the exact original input? Phase 3, finding inverse functions. Let's hit rewind. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. That curiosity leads us perfectly to hitting the rewind button on our mathematical machinery. The formal definition of an inverse function, which you will see written as an f with a little -1 exponent, and we read it out loud as f inverse of x, is the function that maps all the values of f of x right back to their original x values. If our regular function was adding 2, the inverse function takes that result and subtracts 2. Crucially, the range of our original function, our finished products, now becomes the starting domain for our inverse machine. We are literally flipping the script. Now, what's really interesting here is how beautifully simple this looks visually. Remember our mapping diagram from earlier? Look at the arrows for the inverse function. They have literally just reverse direction. We are starting on the right side with the numbers 9, 12, and 15, and we are mapping backward to the left to find -1, 0, and 1. It perfectly visually captures the concept of undoing the original process. But how do we actually calculate this reverse rule algebraically to extract those 3 or 4 marks on the exam? The source gives us a highly reliable 4-step extraction method. This is your blueprint. Step 1, swap out the formal f of x notation and just write y to make the algebra easier to handle. Step 2, this is where the heavy lifting happens and where the majority of your marks are awarded. Rearrange the formula to make x the subject. Move everything else away from x. Step 3, once x is totally isolated, replace it with our formal inverse notation, f inverse of x. Finally, step 4, replace the y on the other side back with an x to give the final general expression. It's an elegant, foolproof procedure that works every single time if your algebra is tight.
Phase 4, combining composite functions. Let's link them up.
So, we've mastered single machines and we've mastered running them in reverse. But what happens when our factory expands? Sometimes the finished product of one machine immediately becomes the raw material for the next machine. This is an assembly line, and in Cambridge math, we call it a composite function. If you see the notation gf of 4, it looks super intimidating, but it's just a sequence. The tactical rule here is you always work from the inside out. It means first find the result of f of 4, then take that finished product and feed it directly into the G machine. Do not try to do it all at once. This leads us directly to the core mathematical rule for composite functions. The range for f of x actually becomes the domain for g of x when you are working out the composite gf of x. In simpler, mission-ready terms, the output of the very first process becomes the exact input for the second process. The machines are physically bolted together. What comes out of one immediately drops into the hopper of the other. To really cement this into your strategy, comparing these methods side by side makes the distinction crystal clear. For a regular standalone function, your method is just simple substitution. F of 5 means drop a 5 into the F machine and see what happens. But for a composite function, the strategy is strictly inside out. For gf of 5, you evaluate the inside f of 5 first. Let's say that gives you an 11. You then take that 11, carry it over, and plug it straight into g of x. It is a deliberate 2-step journey. Let's see how this builds when the examiner asks for the overall algebraic rule for the whole assembly line, without giving you a starting number. In this example, we have f of x equals 2x plus 1, and g of x equals 3x minus 2. To find the general algebraic rule for gf of x, we literally take the entire expression for f of x, that whole 2x plus 1 block, and we substitute it directly into the x spot in the g of x function. So g of x becomes 3 times the quantity 2x plus 1 in brackets minus 2. Expand those brackets carefully. 3 times 2x is 6x, 3 times 1 is 3, then subtract the 2, and you get 6x plus 1. Boom! We just built a brand new, highly efficient master machine. We've covered a massive amount of tactical ground very quickly, so let's lock this in. Your function toolkit now has 4 main compartments to extract maximum marks. First, f of x is just a set of instructions, a mapping rule, not a multiplication. Second, remember your warehouse. Domain is what goes in, range is what comes out. Third, you can always hit rewind and find the inverse using that ironclad 4-step algebra shuffle. And fourth, composite functions are just assembly lines where you must work from the inside out. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. By shifting away from abstract letters and thinking about tangible systems, domains, ranges, and assembly lines, you now possess total strategic control over function mathematics. So, I leave you with this. Now that you are equipped with the complete function toolkit, which mathematical machine will you build, link up, or reverse engineer next? Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep practicing, trust the structure, and I'll see you in the next strategy session. Mission accomplished.